Hey guys, this is chapter 10, video 3. Still talking about gases here. I did calculations in the first two videos with the ideal gas law and the combined gas law. Now I'm just going to kind of go through what's left of the PowerPoint just to give you a better idea of some of the smaller details that are in the chapter that you need to pick up. Again, I'm going to talk you through most of the concepts. I'm not going to work problems in this video since I can't use the chalkboard. But I may make one more video working a few more random problems to follow this one. Okay, so first of all, I need to introduce, I'm on slide 11 of the chapter 10 PowerPoint, so if you want to follow along you can. Need to introduce the idea of standard temperature and pressure. It's typically referred to as STP. It's an acronym. Anytime a problem mentions STP, you're expected to know that for gaseous calculations, standard temperature is 0 degrees Celsius, which of course you can't plug in 0. You have to actually plug in 273 Kelvin.
Okay, I found this on the web.
So 273 Kelvin is my standard temperature. Standard pressure is 1 atmosphere. Okay, now it's important, there are cases like when we get into thermodynamics where a lot of reference values that are given are based off of normal room temperature, which is considered to be 25 degrees Celsius, and then the Kelvin temperature would be 298. Okay, that is a common temperature for experiments to be done, but when we do gases, we refer to standard temperature as 0 degrees Celsius, pretty much because if we want to establish for a given reaction a consistent temperature, and I want to do an experiment here in the United States and somebody else wants to do the same experiment in China or somewhere else around the world, one of the easiest temperatures to achieve is 0 degrees Celsius in a container, because if we just mix ice and pure water, ice water, like whenever you put ice into a liquid, the liquid will cool down to its freezing point. Freezing point of water is 0, so you could easily establish that in a container, the temperature is 0, and that could be consistent around the world. Room temperature changes. Whether you turn on your air conditioner, your heater, whether you go outside or whatever, room temperature is always changing, so that's a much less consistent value for us to use. So, next thing, the question itself actually asked, if we know what STP is, standard temperature and pressure, if we have 1 mole of a gas at STP, what will its volume be? Okay, well, if I have 1 mole, that's N. The standard temperature is 273 Kelvin, that's T. The standard pressure is 1 atmosphere, that's P. We know R is a constant. So it's pretty easy to plug all these things in and solve for V. And if you do that calculation, what you actually find is that the volume of 1 mole of a gas actually comes out to be 22.4 liters. Okay? Now, what's funny about that is nowhere in that problem did we mention what the gas was. Whether the gas is helium or oxygen or carbon dioxide or anything else, the volume that 1 mole occupies of any gas is 22.4 liters if we have STP. Now, why is that important? Well, a lot of times if we do a reaction lab that involves gases, we might set it up so that everything's done at STP, or we might do it under normal conditions where my pressure probably is going to be around 1 atmosphere. The pressure is not going to change very much normally, but the temperature, instead of being 0 degrees Celsius, it might be 298. Or 25 degrees Celsius is actually a little warm. It might actually be 21 degrees Celsius in a room in your house. So that would be like 294 Kelvin. Well, honestly, the difference between 273 Kelvin and 294 Kelvin is not that big of a difference. So when we do reactions, if we want to know for a given reaction how much, like if we're doing a reaction to produce a gas, if the gas is going to fill up a balloon, we know that for about every mole of gas that's produced, the volume of the balloon is going to increase by about 22.4 liters. So if I have a balloon whose volume is around 45 liters, I know that that's about twice this number. So if I'm at normal conditions, 45 liter balloon probably has about 2 moles of gas in it. Okay, so that's just a helpful kind of a shortcut. Instead of doing long calculations, if I know the volume of a container and the conditions are anywhere near STP, I can just say, well, I'll just take the volume, divide it by 22.4, and that's going to give me an estimation of what the moles are. Okay, now, if I'm at STP, take the total volume of the container, divided by 22.4, that will give me the actual volume. If I'm not at STP, but I'm close to it, then it's going to give me more of an estimation. Okay, so there's a difference between whether I'm going to be accurate on that or just get an estimated value. So, what that leads us to, the next thing we have to talk about is, okay, we talked about how, if we have a sample of a gas, how do you calculate the volume or the temperature or the pressure? We use the ideal gas law, the combined gas law, but we need to move into doing stoichiometry. Okay, if we're going to do stoichiometry, meaning we perform a reaction, the reaction produces a gas, and the gas is collected into a container, we need to be able to calculate, okay, what's the volume of that container going to be, or what's the pressure of the gas in the balloon going to be, or whatever. We have to be able to figure those numbers out. So here's an example. If I burn 10 grams of ethanol, so this is a combustion reaction, I should be able to write out a balanced equation for that. Again, for some reason, they balance this with a fraction. It's not normally how we would balance it, but the ratios should still work out. Okay, so that's my balanced equation. I would start my calculation. It says, what's the volume of CO2 produced? So I'm starting with my 10 grams of methanol, which is what was given. Just like in chapter 3 when we introduced stoichiometry, if you have the grams of a compound, the first thing you do is divide by the molecular weight to get the moles. Then you apply the ratio to get from the moles of the thing you're starting with to the moles of the thing that they're asking for. So they gave me methanol, so that's my compound A. They asked me about CO2, that's my compound B. My ratio, compound B over compound A, is 1 to 1 in the balanced equation. So there's my ratio right there, one of these to one of those. That gets me from the grams of A to the moles of B on our mole map. That's all stuff that we did before. There's nothing new there. But now we have something new. I have the moles, but this is a gas. I need to be able to get from the moles of a gas to the question wants the volume. How do I get from the moles to the volume? Well, essentially, I'm going to just plug into the ideal gas law. With the ideal gas law, I have the moles I just calculated, so that's going to go in for N. They told me in the problem the reaction was done at STP, so that gives me a temperature and pressure, and then of course R is a constant. So basically I can plug all the numbers in and I'm going to solve for V. They did that at the bottom, they've already rearranged, and if you solve this yourself, you should get that the volume of the CO2 that's produced is 7 liters. Now, what if I wanted to estimate it? Remember our thing we said before, I have about 1/3 of a mole here. I know that 1 mole would occupy 22.4 liters. So if I have about 1/3 of a mole, it ought to be about 1/3 of 22.4. Or if you take 22.4, divide it by the moles, that's going to give me the volume. So that would be a shortcut I could do. Doing PV equals nRT is like the proper way that shows everything all the way out. Okay, but that's how I would solve that problem. Here's another one. I do a reaction, I'm dropping a piece of zinc into hydrochloric acid. That's going to be a single replacement reaction. The zinc's going to dissolve in, it's going to kick the hydrogen out. The hydrogen gas that comes out is going to be collected, and that's for the volume of the hydrogen produced. This time the pressure and temperature are different. So this time if I use, once I get to the moles of the hydrogen gas that's being produced, if I did the 22.4 as my shortcut, it would give me an estimation. But since it's not SCP this time, that would not give me the actual answer. So this is one where if I want the real answer, I'm going to have to actually use the ideal gas law, plug everything in, solve for V. Okay? So, talking through it, again, you have to have a reaction, just like before. Now this time, it gives me the amount, and again, we're trying to review topics here. It gave me the amount of zinc that I used, so I can set up the calculation starting with zinc. But it also gave me the volume and the molarity of the HCl. So if it gives me the amount of both reactants, That's my bread and my cheese when I'm making sandwiches. I need to know which one's going to run out first. Do I have enough bread to make a certain number of sandwiches? Do I have enough cheese to make a certain number of sandwiches? Which one's going to be right? It's going to be the one that gives you a smaller answer. So I have to work the problem twice. Limiting reagent problem. From the mass divided by the molecular weight, use the ratio. That gets me to the moles. And then once you have the moles, you can just plug that into P-Buchan's nRT if you want to get the volume. Or with the solution, the HCl, I get to the moles by doing the volume times the molarity. So 0.5 liters is my volume times the molarity of the HCl. Liters times moles per liter. The liters cancel. That gives me the moles. Then I use the ratio of HCl to H2 for the balanced equation. That gives me the moles of the hydrogen there. If I did the top part to the moles and then the bottom to the moles, I could compare those two numbers and decide the smaller one is going to be the limiting reagent. And then I could just finish the one that I need to. If you happen to finish both, I would get that the zinc has the capability of producing 12.4 liters of hydrogen. The HCl can produce 13.8 liters of hydrogen. If I work both answers to the final, both problems to the final answer, the smaller one's the correct one. So the answer to this question is 12.4 liters. 13.8 is not possible, so that is an incorrect answer. Now, this slide has a few practice problems. Again, I think I'm going to come back and do another video working more problems on the chalkboard, so I'm going to move on past this one for now. So the next thing, we want to talk about partial pressures, like if I in the atmosphere, which is a mixture of several different gases. By the way, as everybody know, what is the main gas in the atmosphere? If you don't know that, it's nitrogen. Nitrogen makes up about 78% of the molecules in the atmosphere. Oxygen is around 20 to 21%. And then the third most common gas in the atmosphere is actually argon. Usually when we talk about those numbers, we're talking about dry air. Like, 'cause the one thing that changes a lot is the humidity. The amount of water in the air can fluctuate up and down depending on the weather and depending on where you live. But if you have dry air where the water's been removed, you have nitrogen is number one, you have oxygen number two, you have argon number three. Carbon dioxide is actually way down. It's only 400 parts per million, which is a very low molar concentration. So, mole fraction is a way of representing the concentration of the different gases in air. It's a new concentration term that you haven't seen before. It looks complicated, but it's actually a really simple concept. I just told you that in air, nitrogen makes up about 78% of the molecules. So the mole fraction would be the moles of whatever component I'm interested in, let's say nitrogen. So the moles of nitrogen on top over the total moles of all the gases in the air on the bottom. Okay? Now, if I assume that I had a container of air, if it's 78% nitrogen, that means that there's going to be, out of 100 molecules, 78 molecules are nitrogen, 22 are other molecules. So that means 78 out of 100. In moles, if I converted the molecules into moles, it would still be the same ratio. So actually, I would plug in 78 here, I'd plug in 100 on the bottom. If it's 78%, the mole fraction, the only difference here is I'm not going to multiply by 100. I'm not going to put it in percentage. I'm going to leave it in decimal form. So the mole fraction of nitrogen is actually 0.78. The mole fraction of oxygen, if I'm talking about oxygen makes up 21% of the molecules in the air, then its mole fraction is 0.21. Okay? The only time I can't do that is if they give me the percentage in terms of mass. I would have to change my masses into moles and then plug them into this equation. Okay? So let's do a problem or two on that. So Dalton's Law of partial pressures. Basically the idea of this, again, we're about to get to a problem, but all the gases in a mixture, when they're all flying around and hitting the surface, each gas, each individual component of the mixture is going to contribute a certain amount of pressure to the total. Like right now, the air hitting my skin, I can't tell if the molecules hitting my skin are nitrogen or oxygen or carbon dioxide or anything else. When they hit my skin, they all apply force. Really, the difference between them is a certain amount of the pressure comes from nitrogen, a certain amount comes from oxygen, and a certain amount comes from CO2, and then from all the other gases as well. I just feel the total pressure. So the total pressure I experience is the sum of all the individual pressures of the gases. It's a very simple concept. All the gases give a little bit of pressure, but I feel the total. Okay? So that's Dalton's Law of partial pressures. There's the equation. Each gas in a mixture, they all contribute a little bit of pressure, but the overall pressure, P total, is just the sum of all the individuals. Now, this is where the mole fraction comes in. If I have the total pressure of the atmosphere, let's just say normal atmospheric pressure is 1 atmosphere. So that's all the gases together that are hitting my skin, they're exerting 1 atmosphere of pressure. Nitrogen has a mole fraction of 0.78. So how much of the pressure that I'm experiencing is coming from nitrogen? That would be called the partial pressure of nitrogen. It's whatever contribution nitrogen makes to the total pressure. Okay, so the partial pressure of nitrogen, which is the pressure of this one component, A, equals the mole fraction of that component times the total. So all I had to do to get the partial pressure of nitrogen, we just say the partial pressure of nitrogen will equal 0.78 times 1. Which 0.78 times 1 is 0.78. So that means the partial pressure of nitrogen is going to be 0.78 atmospheres under normal atmospheric conditions. Now, this problem gets a little bit more complicated, but mainly it's because they didn't give me a percentage or moles. I'm going to have to do some work on my own. So what I would have to do here, I would have to find my halothane, which is this compound. I'd have to find the molecular weight, divide 15 grams by the molecular weight to get the moles of that compound. Then I would do the same thing for oxygen. Now specifically, oxygen is a diatomic gas. So if I'm talking about the oxygen gas, that's O2. So the molecular weight of that will be 32. So I would do 23.5 divided by 32. I would get the moles of all the components. The moles of the halothane, the moles of the oxygen. Once I have that, so there are my moles of my 2 compounds. The total pressure, I can find them, and actually I can do this 2 ways. I can find the total pressure, the pressure of each gas, and then add them together. Or what they did, the PV equals nRT, when I plug in N, it's the moles of gas, and it doesn't really matter what the gas is. I can plug in the moles of one gas at a time and get the pressure for each gas. Or what they did, they added the moles together, the total moles of gases right here, times R times T, and then they divided the volume over. So they basically solved for the pressure. This gives me the total pressure here because they used the total moles. So the total pressure of the system, this container that contains these gases, the pressure inside is going to be 1.132 atmospheres. Okay, that might not be how I would have done it. I would have actually found, I think it would have been less work to find the pressure of each gas individually and then add them together to get the total. That's an alternative way to do it. Okay, they did it, they found the total pressure first, and then once they know the total pressure, then they found the mole fraction of oxygen. Remember, the mole fraction is the moles of one component over the total moles of everything. So it's the moles of oxygen over the moles of oxygen plus the moles of the halothane. So they kind of basically, what this means is the oxygen makes up about 90% of the molecules in the container. In decimal form, it's 0.901. Okay, but if you want a percentage, you'd multiply by 100. All right, so that's the mole fraction of oxygen. You can do the same thing for halothane. The moles of halothane divided by the total moles gives me this. Now, what you should notice here, if you find the mole fraction of everything, just like when we do percentages, we know the percentages of all the components have to add up to 100%. The percentages of, the mole fractions have to add up to a total of 1. Instead of 100%, we're in decimal form, so the decimal values add up to 1. Now, once I know my mole fractions, my equation, the partial pressure of oxygen equals the mole fraction of oxygen times its total pressure. So 0.901 times 1.13 will give me the pressure of oxygen. So oxygen is contributing to the total pressure here. Oxygen is causing 1.02 atmospheres of that. Again, it's about 90% of the total. The halothane, again, the mole fraction of the halothane times the total pressure, so 0.099 times 1.132, it's only giving off 0.112 atmospheres. Well, there aren't as many of those molecules in the container, so that's why they give off less pressure. But what I experience is going to be the sum of these two. So the sum of my two individual pressures equals my total pressure. Now, next section, kinetic molecular theory. A lot of this is just stuff you need to read. Like in terms of how we do our calculations with gases, there are some assumptions that have to be made. When we make these assumptions, we're assuming that when molecules fly around, if they crash into the wall, we assume that they're not going to stick to the wall, they're not going to react with the wall, they're just going to hit the wall and bounce off. Okay? We assume that when molecules fly around, they're really tiny particles, and when they're flying around, they're not going to have like a big balloon that hits another balloon and they brush by each other and all that kind of stuff. So the volume of the particles are so small, they're insignificant, almost zero. The molecules are moving randomly. When a gaseous molecule flies around, it just flies in a straight line until it hits something. When it hits something, it bounces off and goes the other way. So assuming random motion means they're not like following a certain path and turning, and they're not being attracted and repelled by other molecules. We're assuming that everything's moving in a straight line, and when they hit things, they bounce off. So exert no force means no attractive or repulsive forces between particles. And all collisions are elastic, so everything when things hit each other, they bounce off. No reactions occur. And then finally, the kinetic energy of the particles. If we remember from chapter 5, kinetic energy equals 1/2 mv squared. So this is the same equation. It's just divided by 2 instead of a half. It's the same thing. So if we double the kinetic energy, then that's going to increase the velocity of the particles. Now, when gaseous particles are flying around, it's important to know that the molecules are not all moving the same speed. Not all particles in a sample are going to have the same energy. You're going to have some molecules that have a little bit less energy, so they're going to move slower. You have other molecules that have more energy and moving faster. Okay, so it creates a distribution. It's not a perfect bell curve like we would like for it to be. It's actually what's called the Maxwell Boltzmann distribution, where if I look at one curve, so I'm going to look at the tall curve right here, that would be the distribution of the speed of molecules at 0 degrees Celsius. So in a sample, what we see is most of the molecules on the x-axis is the speed. The symbol mu RMS means the root mean squared velocity. It's basically the average velocity of all the particles. So the average velocity of particles at 0 degrees, 50% are below this point, 50% are above that point. So kind of the mean or the median right there. That's the average for the molecules at that temperature. Some move slower, some move faster, and actually as I go down, there are some that are moving a lot faster, but it's a very small portion of the molecules. If I heat the sample up, so I go from 0 degrees Celsius to 1,000 degrees Celsius, all the molecules speed up, but we're still going to have a distribution. And what happens is the distribution gets wider. So now at 1,000 degrees Celsius, my average speed's probably around right here, which is higher speed, but I'm still going to have molecules that are slow and molecules that are fast. If I go to 2,000 degrees Celsius, again my average shifts to the right. The molecules are moving faster, but I still have slower and faster molecules even at that temperature. If I want to calculate what the speed of the particles is, again, the root mean squared speed right here represents like the average speed of the molecules of a specific gas. It's going to equal the square root of 3 times R, which is 0.0821, times temperature is going to be 298. And like actually, this R is actually different. The R we use in Ideal Gas Law is 0.0821. This is called a thermodynamic R value. It's going to be 8.314. Okay, so when we use this calculation, you use 8.314 instead of 0.082. It's a different version of the R constant. All right, so that's important for you to know. It honestly doesn't come up a lot, but what we see here is that the molecular weight is in the bottom. So if at a certain temperature, if I want to compare two different gases in terms of how fast they're moving, let's say I want to compare in the air, I want to compare oxygen and nitrogen. Which molecules are moving faster? Well, basically the one that had oxygen is a heavier molecule than nitrogen. If it has a higher molecular weight, when I divide by the molecular weight, a bigger number right here is going to make my speed get smaller. And I'm going to divide by a bigger number, which is going to make my result get smaller. So the speed of a molecule is inversely proportional to the molecular weight. As the molecule gets bigger, the speed gets smaller. It's not a normal inverse relationship. It's actually inversely related to the square root of the molecular weight. So basically, if I quadruple the molecular weight, so the molecular weight increased by a factor of 4, when I take the square root, the speed's only going to go down by a factor of 2. Okay, so there is a little bit of an odd relationship there. The easiest way to deal with that is just to plug the numbers in that you're given in a problem. So there's my other R value. Just keep in mind there are 2 R values. When we get to 1212, you're going to see that a lot. And then the last thing, if you ever have to use this equation, I don't expect you to have to use it on the test of the final. It's more just be familiar with it. But if you do use it, the units are important. The molecular weight actually has to be in kilograms. And the reason for that is that my R value has kilograms in it. So for oxygen, which is normally, I would say it's 32 grams per mole, I would have to convert that into kilograms. It'd be 0.032 kilograms per mole. Okay? And then we get one more thing, infusion of gases. Infusion is defined to be the movement of particles through a tiny hole. So if I have a balloon, if you have a helium balloon that's floating, after a few days, you notice that the balloon doesn't float as well anymore. That's because some of the molecules are leaking through the little holes of the balloon. Just the surface of the balloon, there are little gaps between particles, and over time, the molecules can escape. Small molecules are going to escape faster than big molecules. If you take the root mean squared equation for the 2 different gases that we're comparing, say like helium and oxygen, I know that helium's going to fuse faster or escape through the holes faster, but if I want to know how much faster it's going to be, I'm going to plug both of them into these equations, and I can rearrange and get that the rate of effusion of 2 gases is going to be inversely proportional to the ratio of their molecular weights with the square root on them. Okay? Blah, blah, blah. If typically in a problem, there are 4 values here. They're going to give you 3 of the values. You plug them in and solve for the one you don't know. Okay? And that's pretty much how this problem works. So again, I think there's one of those in the Mastering Chemistry that you have to do. And then last topic in the chapter, we talked about the Ideal Gas Law. We talked about all the different assumptions that have to be made with molecules flying around and not interacting with each other. What happens if those assumptions that we're making, the kinetic molecular theories, what if those assumptions aren't true? How does that affect the behavior of gases? Well, if the gases fly around in a straight line and don't bother each other and they bounce off of each other and all that kind of stuff, that's called ideal behavior of a gas. In some cases, the gases might not behave in an ideal fashion, so that's called non-ideal behavior. we need to know what to do. Okay, now for the most part, under normal conditions, when the temperatures and pressure are in normal ranges, so temperatures around 273 to 298, pressures somewhere near 1 atmosphere, under those cases, the molecules of the air are so far apart and they're moving so fast that they don't really do anything interacting with each other. So our assumptions of the ideal gas law all work really well. But if we increase the pressure, so basically what happens is in a sample of a gas, if we put a lot of gas in a container, so there's all these molecules all close to each other, bumping into each other, if they're bumping up into each other more and more, that's when they're going to start actually having some attraction and repulsion between molecules. You might even have some reactions that occur and stuff like that, and that's going to cause the gas to not behave in an ideal fashion the way we've been assuming up till now. Okay, so one place where the ideal gas law doesn't work is at high pressure, because there's so many molecules crunched together that they're going to start interacting. The one other case is going to be if I lower the temperature to where the molecules slow down. If I get down to really low Kelvin temperatures, like getting near absolute zero, the molecules slow down so that when they pass by each other, normally if they fly by fast, they never even see each other. But if they fly by real slowly, that's where the attractive forces between the electrons and protons can start doing stuff and create attraction. Okay, so high pressure, low temperature are the two cases where the ideal gas law doesn't work well. So what do we do? Well, basically we can adjust the ideal gas law to give what's called the real gas law. It's the same equation: pressure, volume, nRT. It's the same setup, but it has some correction factors. The A value and the B values are specific to certain gases. Gases that like to interact with other molecules are going to have higher values for A and B. But for any gas, if we want to know what will it do under non-ideal circumstances, we can plug in the values of A and B, set up the equation. It's a little bit more work than normal, but it's doable. Okay. Purpose of this is just to say, we know how to treat ideal gases. PVOC is nRT. That works almost all the time. There are specific cases where maybe that doesn't work so well. These are really unusual circumstances, but if that happens, we would grab this equation, whatever gas we're using, we find the value of A and B that we need, and then plug it all in and solve for our unknown value. So that's pretty much it. That's the end of chapter 10. We'll have one more video at the end working some problems. Thanks.